Okay. Um, I wanted to start just, I have been reading your reading responses. I will say the reading responses have degenerated a little bit into, well, it was just a nice summary, and I kind of liked seeing, this really wrestle with the material. If you don't have anything profound to say about that section that you read, why not? It's fine with me if you throw in something that you're wrestling and make connections between the philosophy class and this class and try to work it out. That's another perfectly valid thing. I just want to see that you're wrestling with the ideas. I get it that some of the things we did in the that we read about in chapters 8, 9, and 10 are not necessarily new to us because we kind of address them in the context of chapters 5, 6, and 7, a little bit different order than Merman did. But I'm happy to see you make any connections you can. Here was one that I think was maybe in, I can't remember if it was in the chapters 9 and 10 kind of stuff. And I brought it up here because it's an attempt to make a connection between the philosophy and the physics course, but it's a way of using language that we've all fallen prey to several times, including me. Here's a quote from Merman. The relativist says that either interpretation is permissible, provided it is made clear which observer is speaking. I think it's cool that Merman refers to the relativists, which we talk so much about in philosophy. Well, we haven't been, although I have mistakenly said relativism when I mean to say relationism. Okay, Leibniz is a relationist, and those who don't believe in that space or space-time that we're sort of going to now is a real substance would be referred to as a relationist, not a relativist. A relativist is someone, generally, at least in this context, who believes in relativity, who understands relativity. I've been thinking that the principle of relativity, as put in philosophical terms, must rely on a relativist ideal. How could the principle of relativity be defined by an absolutist? Well, I would say Einstein is pretty firmly, now that we've seen the idea of curved space-time, generalizing the ideas of substantivalism and relationism to space-time rather than merely space in the context that we're talking about. Einstein is imagining that space-time is a substance, something that is being curved by the matter and energy that's sitting in it. And so it's something that's out there. It's something that has a shape, whether or not there's something occupying a point in space or a point in space-time, whether or not something interesting happens there. So Einstein is an absolutist or substantivalist. I mean, we can't really ask him in person anymore, but I would think that most people would agree with that kind of thing. But in any case, a relativist is different than a relationist. I've even mixed up those words because, you think of relative, it just seems like, hey, I've got something set up. We're going to say where things are relative to this thing in space. That sounds like a relationist, but that's not the meaning of a relativist and relativity here. Okay, so just to go back to what we were talking about last time, I set up this problem, which is we want to pull all of these effects, the time dilation, length contraction, and relativity of simultaneity, into a more general formalism. And we could have, if you were in a physics class, we probably would have started here rather than starting with those specific effects. But those specific effects are ones that we would have derived from this formalism, and I think it makes more sense the way Merman's doing it to figure out what properties of space and time and measurements are at disagreement with the way we normally think about space and time. If you just develop this formalism, it's like, well, I got a bunch of equations and I'm not really sure what it says. It's just kind of confusing. This contains all of that stuff in it, and we can easily show that the length contraction, time dilation, and so on are in there. Okay, so we're going to imagine comparing two coordinate systems. One is going to be called F, And at least in the way these equations are usually written down, f will be the one that we're taking the point of view of. And it doesn't really matter whether you call your point of view f or f prime, but whichever one is the one that we're going to sort of draw the pictures of as being as if it's at rest, right? The rest frame, that's the one we'll call f. So in this case, this frame f, the IRF, which includes its own coordinate system made of meter sticks. It's got clocks all along the meter sticks. It's got observers near all of the clocks, not just on the coordinate axes, but they have them all over space so they can make local measurements wherever they like. And in this picture, F's just sitting there, whereas this other IRF, F prime, is moving relative to F. And we've decided that although you don't have to do this, it greatly simplifies the equations for the transformation if you make the relative motion of these two frames along, so we align their axes along the same direction, so the y-axes are parallel, the x-axes are parallel, and we make the relative motion between these coordinate systems along the x direction, for example. Could have used y, but we don't want it going in between the x and the y. That just complicates the resulting equations and the derivation. We're going to assume, as always, that in each of these coordinate system, or IRF's rest frame, that all the clocks that are moving along with them are synchronized in their own inertial reference frame, their rest frame. And we're also going to assume that the coordinate axes overlap at some point. In other words, if we go forward, I didn't show any length contraction and time dilation and relativity of simultaneity effects on here. But you know, the one that's moving should be shown as length contracted relative to the other ones. There's some point in time, here we're viewing it from F. At some point in time in F, the X, Y, and Z axes coincide with each other. And by definition, in F, where all the clocks are synchronized, all the clocks in that frame will read 0 everywhere in F. Whereas in F prime, which is moving, we can't really guarantee that because we want them synchronized in their own rest frame, and therefore they're not going to be synchronized here. But we can choose a particular clock read 0. And so we're going to make the one at the origin. X equals 0, Y equals 0, Z equals, or sorry, X prime equals 0, because we're the coordinates associated with F prime, we'll put little primes or apostrophes after. The one that's at the origin, X prime equals Y prime equals Z prime equals 0, we're going to say when the origins coincide, we'll set that one at T prime equals 0. And that means that all these clocks perpendicular to the motion will also read T prime equals 0 at that instant in the F frame. But as viewed by F, these other clocks are not going to read 0, right? Because they're going to be asynchronous in the picture where it's moving. Okay, so that's a lot of assumptions there, but all those assumptions are to make our life easier. So you got to remember those assumptions when you're setting up a problem, that if you're going to use these simplified set of equations that we get, we need to set up our axes in that particular simplified way. Okay, and the idea is, at some point, these are moving past each other. They're not necessarily aligned anymore. And of course, the clocks at the origin both read 0 when they passed. Now they don't read 0 anymore, right? An event occurs at some location in space and at some time. And each one of these could use their set of axes to measure what are the X, Y, and Z coordinates, or F prime, we would call them the X prime, Y prime, Z prime coordinates. And at what time does this event occur? Just an instantaneous flash somewhere in space. They could measure the space coordinates and the time coordinates. And our goal is down here in the lower left-hand coordinate. If we have the coordinates as measured by one reference frame, we want to be able to use those coordinates to predict what the coordinates would be measured in the other reference frame that's in agreement with what we know about relativity. Okay, and so the idea is, because of the way we've set this up, we've simplified things a little bit. We know that rule 1? There's no contraction along this direction perpendicular to motion, and therefore the Y and Z coordinates, which are their axes are perpendicular to the direction of motion, they're going to agree on the Y and Z coordinates of this event, just because there's no length contraction, and we're not talking about any time information there. So That's an easy part of the transformation. The y coordinate in one frame is the same as the y prime coordinate in the other frame, and same for z. But the x and the t are complicated because, well, first of all, this one's moving, right? So its origin is moving, whereas this blue set of axes is going to say, oh yeah, this occurs at a larger x value. But the red set of axes that's moving, it's moved ahead by the time this event occurs. So it's not such a big x because the origin has moved. But also, these meter sticks that construct this are length contracted in this point of view, right? And the clocks are asynchronous. So it's kind of complicated to think about exactly, if I know the coordinates as seen in the blue coordinate system, what the coordinates in the other one will be. Okay, as I said, it's sort of a complicated bit of logic as you commented on in your reading responses, but that's okay. We're going to step through it step by step, see at once that everything hopefully makes sense in the derivation. And we're going to follow Mermin and use a two-step method. The first thing, at least if I remember correctly, this is how Mermin does it. We're first going to sort of scale back our expectations. And let's say, at first, if we imagine that in f, an event occurs not at some arbitrary time, but at what f calls t equals 0. If there's an event that occurs on the x-axis, and let's call its x-coordinate in the f frame x0, so it occurs at y equals z equals 0, let's find the coordinates in the f prime frame. And of course, y prime equals z prime will both be 0 again as well. Those aren't the mysteries. We need to find out what that x prime and t prime are associated with that. And then we're going to use that to get the more general case, but it's easier to step through it in those two steps. So we're working on step 1 now. Here is at t equals 0. I haven't drawn the other perpendicular axis, but I've shown the two x-axes, and I've made them slightly displaced from each other. And we said that by definition at t equals 0, the two origins coincide. So their 0 positions on their meter sticks coincide. Here's the x prime axis. That's the one that's moving at speed v in the plus x direction. And the x-axis is up there. And it's hard to see in the classroom because the screen's a little bit washed out. But the tick marks are closer together on this axis than this one up here. And that's supposed to indicate that we got a moving meter stick. And therefore, the tick marks on the meter sticks are closer together, as seen from the F frame, which is what we're showing here. This is a picture of what would be seen in F, the t equals 0 view in F. Okay? Here's an event that happens on the x-axis. I've shown it a little bit off just to allow us to draw things easily on the x-axis. But here's an event that we're imagining happens on the x-axis at t equals 0 and at position on the x-axis as measured in f, x0. And our first goal is going to be to figure out what is the corresponding x prime location for that. So how do I express x prime in terms of x0? And also, what is the time that this happens at? In other words, another description of this event is, from the point of view of f prime, would be that event happens on the x prime axis at some position that we're going to call x0 prime, and the corresponding time is non-zero because the clocks aren't synchronized here. So this is going, if this one reads 0, because this one reads 0, and we agreed on that, this one's not going to read 0. That's right next to the event, so it's going to occur at a non-zero time. Okay? It's not the most general thing because we're restricting ourselves to an event that happens at t equals 0, as seen in F. But okay, we're going to use that later on. So our goal is to express the x-coordinate and the t-coordinate of this in primed coordinates in terms of the x-coordinate in the unprimed frame and the speed that it's moving at. Okay. So I've phrased this as some sort of voting question. So I want you to read each one of these and help you think about the relationships. Okay. I want to know what x prime, x0 prime is. In other words, what would the coordinate be measured on this axis here as compared to the coordinate that's read off of this meter stick up there that's not moving, because we're taking the point of view here where the blue meter stick is not moving, the red one is moving. How does x0 prime, which happens to be lined up with it on the axis at that particular instant in time, in F relate to x0? Is it equal, larger, or smaller? Those are A, B, and C. Since you don't have voting cards, you can just do 1, 2, and 3 for those. Okay, there's a little bit of controversy in the classroom in that it looks like it was between the B's and the C's, not equal but larger or smaller. Who wants to voice why they voted for one or the other? Okay, Jack's always willing to offer something up. What do you have to say, Jack?
So the function x prime are length contracted, so there can be more of them in the same distance.
That's right. So what Jack is saying is that since these tick marks are length contracted and closer together, the distance between, at least on the meter stick, when someone is assessing where this event occurs at, it's going to be, x0 prime is going to be a bigger number on the meter stick than x0 is on this non-moving meter stick because the axis tick marks have gotten crunched together. And if more tick marks fit in there, more meters are going to fit in there, right, in terms of how they're reading their meter stick. So it's going to be larger than x0. The person in the moving frame is going to read a larger x for this value than the person will in the non-moving frame. And exactly how much larger? Well, it's given by the length contraction. Well, we know it's either a factor of gamma or 1 over gamma. It depends on how you phrase it. But in this case, the distance between the tick marks got smaller, and therefore the distance measured is going to be correspondingly larger, right? It's kind of like the relationship between if your ticks on your clock take longer, then you're going to measure a smaller time interval as having elapsed. So it's either depending on the way the question is phrased, it's either going to be a factor of 1 over gamma or gamma. And in this case, because we're getting a larger x coordinate, we want to multiply by gamma, which is bigger than 1 there. Okay, that's kind of easy. We got our first thing. We wanted to express x0 prime in terms of x0. Now we want to do the same thing for t0, the time that's going to be read on this clock. So here's a second question. How does the reading for this clock that has the question mark on it, in other words, the time at which this event occurs, compared to the reading of the corresponding clock in that frame at 0 over here? Is it ahead of it? In other words, it reads a greater time. Is it behind it? Or the annoying none of the above answer is C, or 3 for us. Seeing a couple of people starting to vote. This has to do with our relativity of simultaneity, right? There's a bus passing by us. How does the clock at the back of the bus compared to the one at the front of the bus? Okay, I'm still not seeing everybody voting, but I'm seeing a couple 2s out there, and I think I agree with the 2s here. It's either ahead or behind. The way we have to think about it is, well, look, from this point of view, where we're sitting here at rest, we've got a bus zooming by to the right, okay? And we said lagging clock's lead, that's the one that's further behind on that bus, that's one here, is going to be ahead of the other clock. The lagging clock leads, the one that's in the rear of the bus is ahead. So since the zeros line up here, this one reads 0. So therefore, this clock should be behind it, and it's going to read, I don't know how to phrase it, but if we imagine these clocks going to have negative times, it would be at some negative time. It hasn't gotten to 0 yet because the one at 0 is ahead. This one's got to be at still some negative value. So I'm going to put in a minus sign there. It's got to be at some value before pointing straight up, right? And how much is it off from this one? In other words, I know this one reads 0 by definition, because we said when the origins coincide, both of those clocks that are present right there where they coincide are going to read 0. If this one reads 0, this one reads some negative time, and I want to figure out what that negative time is. What's the formula that tells us how much off those clocks are? Which one do we use? LV over C squared. So there's a formula that looks like this. I already put the minus sign in there because I know it's got to be a negative time. But the amount that they differ is LV over C squared. So that should be the negative value. So here's a question. What should I put? This is always the question when you see this formula. What do I put in for L? The contracted length. Okay, so on here, I'm giving you a couple choices. Is it x0? Is it x0 prime? Or is it neither of those? Okay, half are voting, half are still thinking. It's between the A's and the B's. Nobody voted for none of the above. It'd be kind of disappointing if I tricked you with that. No, the correct answer here is actually B, or 2, for the way you're voting here. And that is because, here's the mnemonic, and this is important, again, for tomorrow's exam to really get this straight. Here are two clocks being viewed from the point of view where they're moving. And of course, they're not synchronized, because we're always going to say they're synchronized when we view them when they're not moving. The L here always refers to the proper distance between those clocks. In other words, as seen in the frame where they're synchronized, because in their proper frame, we're always going to assume that they're synchronized. Okay? Now, how far is it? In other words, if we slowed down this axis and made it come to rest, what would be that proper distance that we would measure between these two clocks? It's exactly x0 prime, right? Because we would say, from the F point of view, they think this axis markings are kind of messed up here because they're too close together. But the question we want to answer is, so here are some clocks that are asynchronous. The L we use to figure out how asynchronous there is if we imagine those clocks at rest, well, then this wouldn't be contracted anymore, and x0 prime would be the true distance in that proper frame, right? Because that meter stick would now sort of be longer, but of course that longer distance is now correctly measured by x0 prime in that particular frame. So the correct answer is B. So I need to plug that in there. Okay. Now, all I've done here in this is, well, x0 prime is something that formerly was kind of mysterious to us, but we've cleared it up. I already have an expression that relates x0 prime to x0. So I'm just substituting that in here. x0 prime is gamma times x0. And I left all the other stuff the same. All right, that was a bit of work to find the expression for t0, but let me just get rid of the scaffolding. There's the final result we found, and that's the end of our part 1 of the method. We're halfway there, kind of. Okay, that's not what we were asking to begin with. We were asking not that an event occurs at the special time t equals 0 in the frame we're illustrating here, but rather if an event occurs at an arbitrary time in this frame, then how do we get the corresponding coordinates of that event in a different frame? Okay, so we're going to use that to find the general x prime and t prime relations for an event that happens at an arbitrary time t rather than at t equals 0. Okay, so let's put a second view up here, and we're imagining that just between these two views, they're both views in F, so they're views where the blue axis is not moving. A certain amount of time t has elapsed here. Okay, what's happened in that time? Well, of course, the red axis moved forward, so its origin doesn't line up anymore. It's moving forward at speed v, so in that time t, it's moved forward by a certain amount. And we're going to imagine that here a different event occurs now, so this one's at a later time t. It's at some time t, And by definition, it's going to be at some position x on the x-axis, which is the x-axis in F. And our goal is to, first of all, find out what is the corresponding x prime coordinate that goes along with that. Again, notice the origin has shifted. And also later to find out what the time that goes along with it is, right? Because remember, these clocks aren't synchronized, and so we need to figure out what this clock reads and maybe how much this one shifted from it. So we're going to have to think a little bit here. Okay, so the two statements here is the blue one. I know it's kind of small for those of you in the room. The blue axis F is saying an event happens on the x-axis at x and at time t. The red frame, IRF F prime, is saying an event happens on the x prime axis at some coordinate x prime and at time t prime. And so our goal is to find x prime and t prime in terms of x and t. Okay, so let's just step through. First, just because you'll see why this is interesting in a second, here's where the origin has moved to here on, in this new picture at a time t. A time t has elapsed in the blue frame between these. How do you express this coordinate here, where the 0 lines up, with what position on the blue axis in terms of the speed that axis, the lower axis, is moving at, and the time that has elapsed between the upper picture and the lower picture? In other words, it took a time t to get for the origin on the moving meter stick to get from there to there. And it's moving at speed v. So how far did it move, right? In other words, how far measured on this still axis, how far did it move? Yeah, it's just v times t. That's distance equals speed times time, right? Something moved from this location here over to this larger location. It was the origin of the other axis, and it was moving at speed v and a time t elapsed. So this person's just going to say, hey, it was moving at speed v, and if a time t elapsed, this is where the new origin is. Okay, so that coordinate is v times t. Okay, bear with me for a second. That means that because we're saying we're going to call this position x, if this distance is v times t, and this whole distance is x, then if we take the whole distance x and subtract off this distance v times t, we're left with x minus v times t. Okay, why are we interested in that? Well, what I'm hoping to find is this corresponding distance on the lower axis there, because notice that corresponding distance starts at 0, and therefore if I can figure out this distance, that's going to be what that x prime coordinate is. And I don't mean the distance as measured in this frame. Of course, in this picture we might say it's x minus vt, but I mean from the point of view as measured by someone in f prime, what are they going to say this x value is that lines up with that event where it flashes for a second? Well, how is it going to be related to it? Do you think it's going to be bigger than x minus vt or smaller? Yeah, it's going to be bigger. Again, because of the length contraction, those markings on the lower moving one are going to be seen to be closer together. So more tick marks fit in here than they did on this upper axis. If it measures x minus vt on the upper axis, it's going to measure a larger distance on the lower axis. And since this is 0, that's how we should mark this point over there, right? Just by that distance. And the correct factor is either gamma or 1 over gamma. Since we're expecting a larger one, we multiply by gamma, which is bigger than 1. Okay, that's good because we just found out that this distance, by definition, is how we should label this point there, and that's one thing we were after. So gamma, there I've written out the gamma, times x minus vt is the x prime coordinate. And that's half of what we were after for the final thing here, right? I wanted to say, if you know the x and t coordinates of this event in IRFF, how do you get the x prime and t prime coordinates that the red person would measure? And we've already found the x prime coordinate in terms of x and t. This is how you would convert between them. So that's great. Halfway done. The t is just slightly trickier. Okay, so we would also like to know, according to the clocks that are here, there's a clock present right there, what time does that clock read? Given that when they passed each other, it read 0. That's our convention that we're taking there. Okay, so let's utilize what we've already done up above to help us figure out what this is, and we're going to do it in 2 steps. The idea is, here is the corresponding distance on the blue axis, x minus vt, shown as expressed as a distance away from the 0 coordinate there, right? So if I just say, let's mark off a distance x minus vt here, and let's imagine that there's some event that happens there at time t equals 0, just like this was a different event. If this distance is x minus vt, then this marking on the axis there should be x minus vt. That's, if you go 3 meters away from the origin, you should mark that point 3 meters on the meter stick. And everything's moving here, so there's nothing mysterious happening there, okay? Now, how would I figure out, we're going to use this, how would I figure out what corresponding coordinates should be read down here, both for where we are on the x-axis and what that clock would record at the instant that this goes off if it happens at t equals 0 in the f point of view? Well, to get x prime is easy because we already know that. There was nothing special about x0. We said, hey, if the point above, at time t equals 0, if the point above reads x0, then the point right below on the moving axis is going to read this, gamma times x0. So it's the same way here. If the point above reads x minus vt, then the coordinate down here, that x prime coordinate, should be, well, I'm sorry, I'm saying the wrong one. The t prime coordinate here should be equal to the time at which they record this happening is going to be given by this expression. And remember here, x0 was the coordinate that was right above when the event happened. So if we're considering an event here that happens at time x minus vt, what is the t prime coordinate that goes below? We're just going to call that t1 prime. And the only thing we do is take this expression, but instead of putting an x0 in there, we put whatever was above, and it was x minus vt there. I know this seems like it's getting convoluted, but we're almost done here, okay? So the corresponding time here is this negative time right down here. Now, that's important because it tells us, we know that in this view, this clock is ahead. This one's a little bit behind. That's what the minus sign is about down there, right? This clock is a little bit behind, and we already know how much it's behind. Now, and the separation between these 2 points on that axis is gamma times x minus vt, or at least they look like they're separated by x minus vt. It's the same as the ones down here. So whatever the separation is on the clock readings as seen by f at this instant in time is going to be the same as the separation in the clock readings along this distance at this instant in time, because they're both separated by a distance x minus vt, and the clock asynchrony doesn't change as time goes on. Of course, they're ticking off time, but the amount they're off at a later time, if we separate them by the same distance, should be the same. Okay, so this is telling us, t1 prime tells us how far apart the clock that's here reads and the clock that's here reads. And this one is a slightly lower time than the one that reads here. So now our only goal is to figure out how much time has ticked off, and I think I phrased this as a question here. How much time elapses on the clocks in f prime between the t equals 0 and time t pictures in f? In frame f, a time t, by definition, has elapsed between these 2 pictures. How much time elapses on the clocks in f prime between those 2 pictures? Well, it's the time dilation, right? If t elapses in the one frame, then in the frame where it's moving, only an amount gamma, the tick length would get longer, which means the amount of time that elapsed would be shorter, right? So the tick length would be gamma times t. the amount of time that's elapsed would be 1 over gamma times t. So we've got to add that amount of time because it started off at 0. We now know this clock is going to read that value t times 1 over gamma. And we've got to then say, now that I know what this clock here would read, how do we infer what this clock should read? Well, it should be behind by this amount, right? That extra minus sign there. So I'm just going to add that term in. That's going to subtract a certain amount of time off for it to account for the difference. Okay, we're done, except for just a tiny bit of algebra. And I'm not going to bother doing the algebra. All you have to do here is find a common denominator for these two things and combine them together. And a bunch of simplification happens. So I could multiply and divide by this square root over here to put one of those in the denominator. And then we'd have a product of those square roots in the numerator. So we could simplify it. And then we could combine the two fractions together. After the smoke clears, here's what it simplifies down to. T minus Vx over c squared, just the Vx is over c squared, divided by that same square root, okay? And that's what we were after. We said if we know in F some event happens at coordinate x, coordinate y, coordinate z, and at time t, how do we compute what x prime, y prime, z prime, and t prime would be in the other coordinate? What would they measure for the coordinates? And here it is. If you know just the x's and the t's, you can calculate from those what the x primes and the t primes were. We've already got, there's not really much to do for the y's and the z's because of the way we've lined things up. Okay, so that's called the Lorentz transformation. You're transforming coordinates between two frames. If you know what the coordinates are of an event in one frame, you can just automatically calculate it in the other frames. You got to be careful to align and synchronize everything the way we said at the very beginning. So here are all 4 transformations here telling us how to compute the primed coordinates in terms of the unprimed coordinates. I should also say that, a lot of times when people first see the Lorentz transformation, and I was probably the same way when I first learned about this, you get confused because you think, oh, well, one of the frames has to be moving and one of them has to be not moving. And the one that's not moving is the unprimed frame and the one that's moving is the primed frame. But, I could take the F prime frame as not moving, and then the F frame would be moving from that point of view, right? And from the F point of view, if F prime is moving to the right, then from the F prime point of view, F is moving to the left. So the only difference between going from F to F prime or F prime to F is that in one case, they're moving relative to each other in the plus X direction, and the other one, the relative motion is in the minus X direction. If you think about that carefully, that means if I wanted to convert instead of from the x, y, z, t coordinates to the x prime, y prime, z prime, t prime coordinates, suppose I wanted to convert back. Someone gives me the primed coordinates and I want the unprimed ones. All you have to do is switch the minus sign in front of the v to a plus sign because the sign of v is going to change. Or, if you like, you could say, oh, here's a system of 4 equations in 4 unknowns, and I'm going to solve it for x, y, v, and t. That would make it seem really complicated, but if you think of it the other way, it's simple. So this tells me how to go back and forth between 2 systems. All right, that's called Lorentz transformation. And what we're going to do is just to practice with the mechanics. It's easy to get confused, so we're going to look at a worksheet now, problem 1 on the worksheet. And as always, I'm going to put the folks on Zoom into a breakout room. And in fact, let me just do that now. You got it in your email this morning, so look in your email. You've got a PDF, and we're just doing problem 1. I'll come check on you in a minute. So problem 1 is showing, part of it is to practice with using the Lorentz transformation, but it is to show that the length contraction's contained in here. We can actually very quickly see that the length contraction can be gotten by knowing the Lorentz transformation. Same thing's true of the time dilation and the relativity of simultaneity formula. But I just chose this one as it's a way to practice while also showing that this more general formalism contains the three effects in it that we have. So we're imagining we've got a rod in a certain frame where, let's see, how is it phrased here? It's moving to the right from a certain point of view at a speed corresponding to gamma equals 2. So it's going to be length contracted by a factor of 1/2, right? But we're not going to use the length contraction anywhere in this problem. We're just going to use the Lorentz transformation formulae, which are up at the top of the page, so that you have them for reference there. So the idea is, suppose in frame F, at some particular time, as this meter stick is, or this stick is zooming by, we measure at the same time, of course, if we want to measure the length of a moving thing, we have to do both ends at the same time. We measure the locations of both ends at time t equals 0. And the left end we find at x equals 0, the right end we find at x equals 2 meters. So those are two events we're talking about, right? Measurement of the left end and measurement of the right end. We have the coordinates for those events because we're looking at it from the point of view where this thing is zooming by, and we're going to call that the F frame point of view. So we know that x left is 0, x right is 2, and the times for the left event and the right event, I might call those TL and TR, they're both 0 because by definition, when the, well, I think we're going to, at time t equals 0, that's when that measurement was made in F. So the time coordinates that are associated with both of those is stated in there to be t equals 0. Now what we want to do is use those Lorentz transformation equations to figure out what coordinates would be measured in the moving frame, where we're assuming that the axes overlap at time t equals 0, and both the ones at the origins read t equals 0 at that point, and all that kind of stuff. And then in B, you're supposed to calculate what the difference in the x coordinates would be in the other frame and see if it agrees with what we know about the Lorentz transformation, the length contraction. Okay, let's talk about doing it together, because I know the first time you use these equations, it can be kind of confusing. And let me hope my focus problem doesn't work for the board that we had before. Let me just check to see that it is in focus. It looks focused enough. That's good. And let's find some chalk here. Okay. So what do we know about maybe, there are two events. The two events that we're talking about are the measurement of the left end of the meter stick and the measurement of the right end of the meter stick. And we're told some coordinates of where and when those happen in the frame F, where the meter, it's not a meter stick because it doesn't have a length of 1 meter, but it's a stick and it's flying by in the frame F. And we're told about some, let me make sure that you guys can see me here. What are the facts? Oh, still can't see that down here. The facts in frame F. What are the facts in frame F? Well, we're told, so we're talking about two events. I might call them E left and E right. E for event, and the left one means it's corresponding to the measurement of the left end. That's something that happened in space and time, and everybody can see it, sort of a public event. We're told that, so there are going to be some coordinates for E left, that left event. It's going to have an X coordinate, which I might call X left. I'm not going to put a prime on it because it's in the frame I'm going to call F, the one in which the stick is seen as moving. Where did it happen? Well, it happened at 0 meters. That's what we're told. What time did that left measurement happen at? Well, we're also told that it happened at t equals 0 in that frame, right? So t left is 0. Let me just make sure I still have room to draw here. There's another event that I might call E right that corresponds to the measurement of the right end. And it has coordinates X right, and I think we're told it's 2 meters. Yeah. And it still happens, I'll call the time that happens 0. Okay, so that's the information we have in F. We've got all the unprimed coordinates. And now we just go to the formulae at the top of the page and start turning the crank. I can calculate what the x prime and t prime coordinates are for each of those events individually. I only want to use this x prime in terms of x and t separately for the left event and then separately for the right event. Okay? So let's now start thinking about, in the frame F prime, what are they going to measure for the coordinates, the x and t coordinates? Everything happened on the x-axis, so the y and the z coordinates aren't very interesting here. Well, let's just go up to the formula at the top. If I wanted to calculate the x coordinate for that left measurement events in the primed frame, I would indicate that by x left prime. And then just copying the equation that we have up at the top, let's see. It looks like we have an x minus vt, so that would be x left minus v times t left. I'm putting the L subscripts on there to remind me that they correspond to the left measurement event. We're going to do a separate calculation for the right measurement event. And then 1 over that square root is the same thing as gamma. In this case, gamma is 2. Right? So let's just substitute what we know in there. Gamma is 2. X left, I'm just looking up above, keeping track of things. X left is 0. V in this case is 0.866 C. But T left is also 0. So that, sort of annoying number is multiplying its own 0 there. So 2 is multiplying just 0 there. And so that means the coordinate of the x left end measurement, that event, in the prime frame is also going to be 0 meters. Okay, I'm just going to put a box around it because that's sort of one piece of several pieces of information we're interested in. While we're talking about the left measurement event, let's find out what time it happens at. Let's call that t left. That's the time that that left measurement event happened in the prime frame. That's what the notation means. And looking at the formula up at the top of the sheet here, that's equal to gamma times t left minus v times x left over c squared. Okay, let's substitute into that. Gamma, again, is 2. That's kind of nice because I chose v the right way. T left, again, I look up above, that's 0. Minus v is 0.866c. X left is, again, 0. Who cares if I divide by c squared because I've already got a 0 there. And so this one ends up being 0. So I could write that as 0 seconds because I know it's a time. So that's where and when the left end measurement event happened in the prime frame. Not so exciting because it was at 0, 0 in the one frame and it was at 0, 0 in the other frame. That just happens because I put something at the origin. When it's not at the origin, we'll find the other one's not so trivial. So let's now talk about the right end measurement event. Let's find its coordinates in the prime frame. What I might call x right in the prime frame. Where on the x prime axis does the right measurement event happen? Same formula. It's gamma this time times x right minus v times t right. Notice I'm always sticking with the same event here. I don't want to mix up the lefts and the rights. They're different events. This tells me how to transform one event from one frame to another. So we have to stick with the coordinates just for that right measurement event. Okay, gamma is 2. X right, looking up above, that's 2 meters. Minus v, 0.866c, times t right. Well, t right's still 0 because everything happened at t equals 0 in the f frame. And so I don't really have to worry about the second part. It's just 2 times 2 meters, which is 4 meters. Okay, and then finally, the last piece of the puzzle is when did that right edge measurement happen in the as seen in the prime frame? One more time, gamma times t right, I'm just copying this over again with the lefts changed to rights, minus v times x right over c squared. Let's expand that out. That gamma is 2, t right is 0, minus 0.866c is v, x right is 2, and then I've got to divide by c squared. Now I've got a c over c squared, so I can cancel this c in the numerator against one of those two factors of c in the denominator, just leaving me with 1c. So it looks like the number I've got to calculate is 2 times minus 0.866 times 2 again, and then divided by 3 times 10 to the 8th, because I've still got a factor of c there. And when you do that, of course, you're dividing by a big number, so you're going to get a small number. And it's negative because of this minus sign here. I get minus 1.15 times 10 to the minus 8 seconds. 11.5 nanoseconds with a minus sign in front of it, if you wanted to express it that way. A very small amount of time. Okay, so now I've just translated the coordinates at which two events would be measured in one frame into the other frame, just very mechanically. You just got to know how to use those formulas, and I'm doing nothing but turning the crank there. No intuition required. Questions on A. That was just A. Now, B, we're asked to calculate the difference between the right coordinate and the left measurement coordinate in the primed frame. In other words, how far apart did those two events occur? Well, if we do x right prime, that's 4 meters, minus x left prime, that's 0 meters. 4 meters minus 0 meters. X right prime minus x left prime is 4 meters. And the question is, does that accord with your understanding of the length contraction? Yes or no? Yes, well, I'm giving some head nods and thumbs up signs in here. And that's because, look, the primed frame, in this case, we're taking the frame where it's moving along with the meter stick. That's by definition what our primed frame was. We didn't have to do that, but in this case, we're trying to do the length contraction. It should have a bigger length when measured when it's sitting at rest than when it's seen moving by. And gamma equals 2, notice that the length as measured in the prime frame is exactly different from the length as measured in the unprimed frame. The difference in these two coordinates was 2 meters. And that's exactly what we expect in this case. Okay, so B, the answer is 4 meters. And yes, that agrees with what I understand about length contraction. Hopefully you can think about it that way. We expect its proper length to be greater by a factor of 2. Its length contracted in the original frame that was described. C brings up a little worrisome bit here because look, the problem with this is, okay, these two coordinates of the left and right end measurement agree with the length contraction, but they technically happened at different times in this frame. And I've been making a big deal since the beginning that when something is moving by you, you better make sure that you measure both ends at the same time or you're not getting what we call length, right? If I measure the back end first and I let the front end go ahead and I measure it later, I'm messing up. That's not what we mean by length. You have to measure them at the same time. Why don't I have to worry about that here in this particular case? Why is it okay that, even though this is a small difference in time, if something's moving, if it's moving close to C, it could actually go pretty far in that amount of time. Why does it not matter, Jack? Okay, so this is the time, it's still true that the left and the right ends were measured at different times. So I'm trying to listen if you're giving a clear explanation for why it doesn't matter that I'm measuring the left end and the right end at 2 different times in this frame. Yes? No, not necessarily. Even if these had been some non-zero time up here and the left end had been not at the origin, we still wouldn't have this problem here. I was just trying to make your calculations easy by putting a lot of zeros into it so we wouldn't have to calculate so much. What does the F prime frame mean in this problem? The F prime frame is the frame at which we're moving along with the meter stick. It's the frame in which the meter stick is at rest. If you're trying to measure the length of something and that thing is at rest, does it matter if you measure the one end and the other end at different times? No, that's the only time it doesn't matter. And so it's because, by definition, we chose the F prime frame to be the proper frame of the meter stick, the frame in which it's at rest. So even though the times we made those measurements were different, as long as the thing isn't moving in that frame, it doesn't matter. Just like when you measure the length of a piece of paper, you usually measure the left end and then you measure the right end and you subtract. But that's okay, because you always do that when it's at rest. It's when it's moving with respect to you that you have to be careful to do it simultaneously. And that was the case in the other frame when it was moving. We did them both at t equals 0 in that frame. Okay, so that's a little bit of an introduction of how to just use mechanically those Lorentz transformation formulae. Any more questions on that worksheet? Okay, that doesn't necessarily show you the utility of the Lorentz transformation because we're reproducing something that we could have done much more easily before, right? That would have been much easier to do that whole thing with the the length contraction formula. But at least we showed that it's contained in it. Okay, and let me turn out the lights in here again and share my screen. Now, in previous semesters, I should say, the last time I taught this course. There was a lot of complaint at this point because it seems to be saying that to use this, one of your frames has to be at rest, and the other one's the moving one, right? The primed frame is the rest frame, and the unprimed frame is the rest frame, and the primed frame is the one that's moving. And people sometimes say, well, wait a minute, that doesn't agree with the principle of relativity, because nothing's fundamentally at rest. If I've got a bunch of frames that I want to compare, how do I know which one I should take to be at rest? So we're going to imagine some place where we don't have any sense of what rest and motion even mean. So let's just think about sitting in deep space. Ignore the little pictures at the side of the screen. Everything's black. There's nothing being displayed on that central part of the screen. Uh-oh, I've lost contact with my remote. Let me click over here. Okay. We're far from anything. We have no points of reference. I don't know what's moving and what's not. We're just looking out in front of us, and all of a sudden, oh, there's something that moved by. Okay, that's something I might be interested in measuring. Is it at rest or is it moving? I don't know. It seemed like to me it was moving, but who knows? Oh, there's something else. Maybe it's the same rocket. Maybe it's a different one. I want to make some measurements of it. How do I get these meter sticks and these clocks to make the measurements of it? There's an event that happened, that little flash. There's another event that happened. How do I know the coordinates of those events? I don't have any meter sticks. Am I at rest? I don't know. The answer is it doesn't matter, because I can just hold out a meter stick in front of me, and I don't care that I'm at rest or not. But that meter stick is what that's what I'm going to use if I'm interested in finding out what the coordinates of someone on the spaceship would measure for an event versus me. Here I am, I'm holding out a meter stick. That's going to be like my meter stick that I'll use for the F frame, and then the one that's moving by maybe for the F prime frame. Okay, so that spaceship moves by. Now I've got a meter stick at least, but I can't really measure its speed because I don't have any clocks on it. So I got to put some clocks on it. Of course, I'm going to synchronize them. As the spaceship goes by, maybe it's got a clock on it, but I still can't see the relativity of simultaneity. So maybe I want to have something going by that has a bunch of clocks, and now I can see that they're asynchronous, right? In fact, more generally, I might want to build up a whole scaffolding corresponding to that ridiculous picture we showed at the beginning of the course for a fanciful IRF, right? I'm going to have clocks and meter sticks everywhere, and I'll build up a huge three-dimensional coordinate system with local observers near every one of those clocks. And if something goes by and an event happens, I can really get it nailed down. In fact, if I'm interested in comparing my point of view to the point of view of something else, I might want it to have that same ridiculous coordinate system and set of clocks moving along with it. So, for example, if that rocket goes by and there was a little flash, I don't know if you saw that, but that flash is an event, and I want to know in my coordinate system what the coordinates of the event are, including the time, compared to what it was in that ship. So here it is. If it stops right there, sorry, I'm checking my phone because I just need to make sure it's not an emergency from the family. Okay. So here I've stopped it right when that event is flashing, and I would like to know, I haven't illustrated all the effects on here, but my clocks, of course, would be synchronized. These ones should be somewhat asynchronous with respect to each other. And I'm imagining this is farther away, so it only appears smaller, right? But our goal with the Lorentz transformation is, I don't need to know who's at rest, right? I'm just comparing one point of view, and you can take that to be my point of view and somebody else's point of view. And all I need to know is the relative motion between the two. So for example, the way we've set things up is a little bit more nicely. We said, I'm going to have my axes. I got to specify where the origin is. I know it's hard to see in the room because of a little bit of the light here, but this is my x-axis here, and this is labeled as the y-axis going up there. And here's somebody coming by. And at that point where the axes coincide, we're going to call that t equals 0. So I'm going to set all my clocks to t equals 0. And you'll see there's a little event that flashes in there, we want to compare what our coordinates are for that. So if I go forward and stop the movie right there, where that happens, I'm trying to compare those coordinates. There's no sense in which somebody is fundamentally at rest, but you just take someone's point of view and assume that's the F1, and then you'll be able to translate into what you expect the other person to measure for the coordinates of this little flash that we're showing right here. Of course, their x coordinates are going to disagree. Their origins aren't even at the same place. So of course their x coordinates, not only are their origins not at the same place, but their scales, one of them is contracted, and some of the clocks aren't even synchronized, so it's all messed up. But this Lorentz transformation tells us exactly how to take all that stuff into account and translate between the set of events. Okay, so again, if there's an event and we want to know if we know the coordinates of that event in one reference frame, in other words, we measure its x, y, z, and t coordinates, the t coming off the clocks, whatever clock is nearest to that event. I could get its coordinates in some other frame that's moving with respect to that frame. And in this case, if it looked like this in the picture, the x prime coordinate would actually be negative here, right? If this is the plus axis going over here, this would be a negative x coordinate, but a positive y prime coordinate there, okay? This is all, it's easy to forget, but you have to do all three of the things that we said we were going to do at the start. Synchronize all the clocks in their own ref frame, make sure that one moves with respect to the other in the plus x direction, and set the clock times to be equal to 0 at their origins when the origins coincide. That's when t and t prime are 0 at that location and that time. Okay, so as we're going forward, some event happens, and we're going to measure it from those point of view, those 2 points of view. This was not a reading response question from you guys, but it was something that sometimes people ask about, and I think I kind of alluded to it already. What would we do for the case where they were moving diagonally with respect to each other? Do we simply rotate the coordinate system so the x-axis is parallel with the motion? And the answer is yes. If we want to use this simplified form of Lorentz transformation, we need to do that. You could write one that allowed for arbitrary motion, and it would be a huge mess. It's better to just to align the x-axis. You know, you say, I know what's happening in one point of view, and I want to know another point of view. Let's make the direction that other one is moving with respect to the first one plus x, and then you can use those Lorentz transformation formulae directly. Okay, Merman makes a big point about he strongly prefers using rules 1 to 5. And here again, this is not from your comments, although several of you said I do like the rules 1 to 5 better, probably following along with Merman. But it would be interesting to see a situation in which this is not the case, or here someone down below is saying, are we to only use this method when trying to find out when an event happens when we have the coordinates? Yes, when the event would be measured to happen in another coordinate system. And so the first problem that we did, and we're not going to do the second problem on the sheet now because we're essentially out of time. The second one shows the utility of the Lorentz transformation above and beyond our length contraction, time dilation, and relativity of simultaneity formulae. In other words, the second problem has to do with, in one frame, I don't care whose frame it is, a flash goes off over here, and then later on a flash goes off over here, and we get x, y, z, and t coordinates for those two flashes, right? So there's a certain time delay between them. There's a certain distance between them. And the question is, what is the time delay and the distance between them in the other frame where we're told how fast it's moving with respect to it? And of course, both of them change. And that's something that is not easy to get at with just the length contraction, time dilation, and relativity of simultaneity formula. You'd have to apply really all three of them to be able to figure out that difference. It's much easier to use Lorentz transformation. So we'll try that second problem at the beginning of Friday, I guess. Because tomorrow, once again, we're meeting at 9:10, and we're starting that exam. Covers the material on 5.